All right, so we have in this one, same directions. Does it converge? Sum n equals 1 to infinity, negative 1 to the n, square root of n divided by 1 plus 2 times root n. Okay, so you guys tell me, what do we write down first? Bn. What is Bn? Right, 1 plus square root of n divided by 1 plus 2 root n. Is it bigger than 0? Yeah. And then, for the n that matters is from n equals 1 to infinity. So for n greater than or equal to 1. Okay. So we need to first show that the limit of the Bn, in order to get convergence, that is, we need to show that the limit of Bn as n goes to infinity is what? We need to show that that limit's 0, right? Yeah, I was actually stating the second criteria. If you suspect that it's not going to converge, you might want to just look real quickly at that and talk about that second criteria. And ignore the first one. Why would I want to do that? Well, I notice right away that Bn doesn't converge to 0. Okay, and if either one of them is not true, you might have yourself a sequence that doesn't converge. Specifically, if 2 is not true, it's not going to converge. So what does the limit, in other words, I'm saying the order here, criteria 1, criteria 2, doesn't matter. What does the limit as n goes to infinity of the square root of n over 1 plus 2 root n, what does that equal? Yeah. If you want to prove that, yeah, you could resort to L'Hopital's rule, but it's actually pretty quick to go 1 over square root of n, 1 over square root of n, like that. And then you get, what, 1 on top? 1 over root n. I'm going to put the limit symbolism in there in a second. 1 over square root of n plus 2 on the bottom, and then don't forget the limit symbolism. And then I think it's pretty clear, as n goes to infinity, this guy goes to 0, and you get 1/2.
Are you allowed to just think of the square root of n as n to the 1/2? And then
Yeah, it wouldn't be be able to do it the way I showed you, but in this one, yeah, I'd be pretty flexible about that if I didn't state any directions otherwise. So that's not 0 last time I checked, right? 1/2 is not 0. So this does not equal 0. Well, okay, Bn isn't quite An, is it? So what can you conclude about An if Bn, this is An, if Bn doesn't converge to 0, it converges to 1/2, what can you conclude about An? So An gets closer to 2 numbers as n gets big. So the 2 numbers are 1/2 and negative 1/2. Right? Because it's an alternating series, right? So An gets closer to 2 numbers, 1/2 and negative 1/2, as n goes to infinity. Thus, An does not converge to 0. I'm going to use the arrow notation with the slash through it. Oh, so what test do we actually use to show divergence here, since An is not converging to 0? It's not AST. What is it? So remember, in order for a series to converge, have a chance of converging, let's put it that way, An must converge to 0. Right? Otherwise, you keep adding a bunch of non-diminishing terms. Oh, but we stated it the other way around. We said if An does not converge to 0, then the series diverges. What test did we call that? Anybody remember? Yeah, I call it the nth term test. I think your book calls it the test for divergence. I call it the full name is the nth term test for divergence, whatever. So if you say the test for divergence or nth term test, I'll know what you mean. Yeah. So we're ready for the conclusion then. So the original series, or just the series, diverges by the nth term test. Okay, so take a look at that. So what were the components of that test? Well, notice I kind of made my conclusion right away. That thing's diverging. Why? Because I recognize Bn as something that doesn't converge to 0. And you want to train your brain to look for that right away. Does the An or the Bn in this case converge to 0? If not, then the proof almost writes itself. So I didn't bother seeing whether or not Bn decreases. I went right to the fact that the limit of Bn is equal to 1/2, which is not 0. And then right away you can make a conclusion that looks like this. If Bn doesn't converge to 0, An is going to converge to two different numbers, always. Whatever Bn converges to and the opposite of whatever Bn converges to. Or if you get like Bn diverging to infinity, then An is going to diverge to larger and larger numbers and smaller numbers, right? Absolute value-wise, in other words, An diverges to infinity, but it alternates between numbers going to positive infinity and numbers going to negative infinity. So either way you look at it, the An is not going to converge to 0 either. And so you actually make the conclusion by the nth term test that the series doesn't converge.